Welcome to the video on Graphical Behavior Day 2. In this video we're going to be covering the use of concavity to determine extrema. And in Day 1 we learned that we can use the second derivative to determine if a function is concave up or concave down. And now what we're going to do is we're going to use that second derivative to determine whether we are reaching a local minimum or a local maximum. So this is another way that we can find extrema on a function. Okay, the I can statement. I can use the second derivative test, so that's the test we'll be running, to determine the location and value of local extrema. So the second derivative test is fairly similar to the first derivative test. They're both used to determine local extrema or relative extrema. And the way the second derivative test runs is first we need to use the first derivative to identify the critical values. And then once we know the critical values, what we do is we plug them in to the second derivative. And if the second derivative is positive, what we wind up having is something that is both flat and concave up. Therefore, that is a local minimum. Alternatively, if we take our critical values and we plug them into our second derivative and we find that our second derivative is negative, that means the function is concave down, and we've got a spot where the function is both flat and concave down, giving us a local maximum. And then finally, if the second derivative winds up being equal to 0, the test fails and we need to rely on the first derivative test to determine if it's a local max or a min. And real quick, a refresher on the first derivative test is you would stick your critical value into the derivative function, and that's the one where if it goes from increasing to decreasing, we have a maximum, and if it goes from decreasing to increasing, then we have a minimum. Alright, without further ado, let's try this out on example 5a. We're going to refresh ourselves with the first derivative test, and then we'll go on and use the second derivative test to prove the same thing, if possible. So what we have is a function, a nice polynomial, so it's continuous everywhere. And if we take the first derivative, we're going to get negative 15x to the fourth plus 15x squared. And we'll set that equal to 0 to find our critical values. So if I factor out negative 15x squared, I'll get x squared minus 1, setting that equal to 0, and I see that there are critical values at x equals 0 and plus and minus 1. So now that we have the critical values, we can run the first derivative test. So we create our number line and we test f prime in this. And we find that if we stick a number in there like negative 2, we'll get, what is that? That's a negative answer. So it's decreasing there. Plug in 0.5 and we'll get a positive answer for both negative 0.5 and positive 0.5. And then finally plug in something like 2 and we find that this is negative. So we have a function that's decreasing, increasing, increasing, decreasing. So by the first derivative test, we have a local min at x equals negative 1, and we have a local max at x equals 1. And since the question asks us to justify it, we need to include a justification. Using the first derivative test, f prime changes from negative to positive, giving us the local min, and f prime changes from positive to negative. So there's the first derivative test, a little refresher on it. Now let's see how this runs with the second derivative test. So if we have f prime, which we do, we can find out our our second derivative from that. The second derivative will be negative 15 times 4 is negative 60x to the third plus 30x. And we're going to use the second derivative. What we will do is we will test all of our critical values, which we found above in part A, our critical values. We're going to test them all in the second derivative. F prime prime of 0 and F prime prime of 1. And if we plug negative 1 into the second derivative, we get an answer of 30, which is greater than 0. And since the second derivative is positive, we're concave up there. If we plug 0 in, we will get 0. So we don't know what's going on. Well, it's neither concave up or concave down. And finally, we stick 1 into the function, and we get negative 30, which is less than 0. Therefore, we are concave down. Drawing our conclusion by the second derivative test, we have a local min at x equals negative 1 and a local max at x equals 1. And if you don't remember the name of the test, you can always create alternative justifications, which is using what you found. So we found a min because at x equals negative 1 because f prime of negative 1 equals 0 and f prime prime of negative 1 was greater than 0. So that tells us the function is concave up and flat at that point. The justification for the second one would be f prime of 1 was 0 and f prime prime of 1 is less than 0, which tells us that the function was concave down and flat at that point. Okay, example 6, we're going to talk about graphical behavior using the table above, and what we have is we have specific values of the function, the derivative of the function, and the second derivative. And just for practice, what we can do is we can go through here and we can say various things like, because the second derivative is positive, we're increasing, we're flat where it's 0, and we are decreasing here. And then going to the second derivative, what we have is concave up, and then concave neutral, or neither up or down. So that's always a useful tool to go ahead and write that into the table. Okay, part A, is it safe to say that the function is concave up on the interval -3 to 5? So while these values excluding the endpoint are positive, we can't guarantee that the function is concave up because it's possible that like f prime prime of 1 is a negative answer. So if that's the case, we can't determine that it's concave up everywhere. So the conclusion is based off of that, we only know the value of f prime prime at specific locations. So the value of f prime prime is only known at -3, 2, and 5. As such, it is possibly, or it possibly can be, and be negative elsewhere. Okay. Explain why there must be a z within the interval of -3 to 5 such that f of z is 6. And this is reviewing, do you recall the IVT? And between -3 and 5, it's possible, very specifically, even between 2 and 5, that a 6 will occur because we start below 6 at 2 and finish above 6 at 7. So the IVT guarantees it. The function is continuous, so we can use the IVT. So we use that and we state, since f of x is continuous and f of -3 is equal to 0, which is less than 6, which is less than 7, which is f of 5. Conclusion, there exists a z in -3 to 5 such that f of z is equal to 6. So that's just reviewing the intermediate value theorem. Part C. Explain why there must be a number w such that f prime of w is equal to 7/8. So this is reviewing the mean value theorem. And if we find the average slope from -3 to 5, we'll do f of 5 minus f of -3 over 5 minus 3. That's 7 minus 0 over 8. So our average slope is 7/8. So the mean value theorem will guarantee that somewhere the slope of the function is 7/8. So since f of x is continuous and differentiable on -3, 5, the MVT guarantees a w in -3 to 5, so some value between -3 to 5, or such that the derivative at that point, the slope at that point, is equal to the average slope of 7/8. So stepping off to the side, if you remember, what's going on here is we have a function, and whatever it does, if our slope from one endpoint to the other endpoint is 7/8, the MVT is guaranteeing that somewhere else a tangent line will have a slope of 7/8. It doesn't tell us where, and it doesn't tell us whether or not there's more than one spot that has a slope of 7/8, but it does guarantee there is at least one spot. Okay. Finally, does f of x have a local maximum, a local minimum, or neither at x equals 2? And so we want to go take a look at x equals 2, and we see that at x equals 2 the function is flat, so that's a possibility for a max or a min, or even neither. But then we go to the second derivative, and we see that the second derivative is positive. So what we have is a case where the function is concave up and flat at x equals 2. So because of that, we can see that it's a local minimum. We're using the second derivative test. We can justify that. So f of x has a local minimum at x equals 2 because, and the conditions of, or the reason is because the first derivative at 2 is equal to 0 and the second derivative at 2 is greater than 0. Therefore concave up. So there's our conclusion. Okay, so that's the video for the day. Just to recap what we learned that if we have a curve and the curve has a flat spot determined by f prime being equal to 0, and the curve is concave up, we can determine that there is a minimum. Alternatively, if we have the case where there's a flat spot on the curve but it's concave down, we have a maximum. So that's the second derivative test. Just to reiterate the point, both the first derivative test and the second derivative test are used to prove the existence of local maximums and minimums. All right, thanks for watching.